light reactions. Remember, photosynthesis is mainly occurring in two phases. Don't forget, we said we have what we call the light dependent stage and then what we call the light independent stage. So light dependent stage, as we are going to see, is mainly focusing on light. So our idea today, we are going to base on what we call non-cyclic photophosphorylation. Now when you look at the light reaction or light dependent reaction, they are mainly subdivided into two. Members, don't forget that we have the cyclic photophosphorylation and then the non-cyclic photophosphorylation. So as I'm driving the different lessons, you shall learn one by one. But today, allow me to only consider what we call the non-cyclic photophosphorylation. Now, when we are looking at the non-cyclic photophosphorylation, remember, it is also occurring in the chloroplast. Now, the non-cyclic photophosphorylation is going to be driven mainly by what we call the electron acceptors and photosystems, and then what we call the electron transport system. So we have majorly the components. We are going to look at what we call the photosystems, then we are going to look at electron acceptors, then we are going to look at electron transport system. But the overall process, members, what we are going to yield from non-cyclic photophosphorylation, the main ones which we need in the darker reaction now, is what we are calling the ATP as well as the reduced NAD. Now those two components are very, very vital because we always apply them in the darker reactions like the Calvin cycle as well as the Arch and Slack cycle. Remember, Calvin cycle, we shall see it in the C3 plants, then the Arch and Slack pathway, we shall see it in the C4 plants, and so on. Remember, even CAM plants will apply some of the ATP and the NADP H, which we have yielded from our non-cyclic photophosphorylation. Now, when you look at non-cyclic photophosphorylation in details, after understanding that is simply the formation of ATP from ADP and inorganic phosphate in the presence of light, we are going to begin by seeing when you look at the notes moving on your screen, you'll discover that the chain itself is having two photosystems. It's having what we call photosystem 1, that is at 700 nanometers. That is the photons of light which it can absorb. Then when you follow up the notes which you are seeing on your screen, you will discover that even there is what we call photosystem 2. Photosystem 2 at 680 nanometers. Now when you say 700 nanometers, it means now that is the wavelength. Bigger wavelength you can see. Then longer wavelength now with now lesser energy. Then when you look at 680, that is shorter wavelength with bigger energy. When you look at energy scale represented on that diagram, the sequence diagram by the arrow. Now what are we going to see in this non-cyclic photophosphorylation as we are checking your notes there? We are going to see that the photon of light, when it strikes photosystem 2, that is at 680, we see that electrons from the chlorophyll molecule now, they are going to become excited from a lower energy level, that is from photosystem to the higher energy level. Now as they are being excited, their electrons are going to be accepted by what we call plastoquinone as a primary electron what? Acceptor. So what happens now after electron is being excited? At the same time, there is a reaction taking place at the same photosystem, what we are calling photolysis or Eru's reaction. In photolysis, the water, as light is striking the water molecules are going to break down. When the water molecule breaks down, it releases the hydrogen ions, which you are going to see later, which are going to be used to form reduced NAD. And with some oxygen, this oxygen is on which we give out as a as a byproduct. During photosynthesis, don't forget that the whole equation produces oxygen as a byproduct. The oxygen as a byproduct, members, is not coming from another point, but is coming from this point of photosystem 2 as a result of the breaking down of the water molecule, which we are calling photolysis or Eru's reaction. Now the electrons which were lost as a result of the excitation are going to be replaced by electrons from the water. That diagram is going to show you clearly. As electrons are being excited, some electrons are entering at the photosystem 2. Now, we are seeing our electrons already have been received by plastoquinone as primary electron acceptor. After being accepted by plastoquinone. Plastoquinone now adds the electrons to what we call the electron transport system. This one is mainly made up of conjugated proteins known as cytochromes. Now cytochromes now are going to pass the electrons downwards to photosystem 1, which is at 700 nanometers. Now, those electrons, as they are moving downwards from higher energy level from plastoquinone to a lower energy level to what we call photosystem 1, we see that some energy is being lost. The energy which they are losing, the energy which they absorbed as they were raising from photosystem 2. Now we are seeing that they are losing that energy. As they are losing that energy, the energy they are losing is going to be used in members, don't forget that, to accelerate the combination between ADP and inorganic phosphate to form our ATP. Are you seeing that? ATPs from where? The ATPs are rising from the inorganic phosphate and ADP. And the intermediate now, the accelerated catalyst is the energy now, which electrons are losing from higher energy level to lower energy level. Now those electrons are going to replace the electrons which were excited from photosystem what? Photosystem 1. Remember, light is striking both photosystems, photosystem 1 and photosystem 2 at the same time. Now, as light is striking on them, as electrons are being excited at photosystem 2, that is at 680 nanometers, electrons are also being excited from photosystem 1, that is at 700 nanometers. Now, we are seeing even electrons of photosystem 1 are being excited. They are raising higher energy level. But now, those electrons which were excited from photosystem 1 are going to be replaced by those electrons now which are coming from the plastoquinone. Are you getting that? Take note, the electrons from plastoquinone are not being excited upwards for ferredoxine, but again they are replacing those electrons which were excited from photosystem what? Photosystem 1. Now the electrons of photosystem 1, as they are raising their energy level, they are going to be received by what we call ferredoxine as another primary electron what? Acceptor. Now from ferredoxine, those electrons are going to be passed through the electron transport system of the cytochromes to be added to what we call the NADP. To be added to what we call the NADP. Now, as the electrons are being added to the NADP, there is still some energy because they are seeing they are moving from higher level to lower level. High level, lower level. Now, the energy there is going to be now used to form what we call the NADP-H. Now, NADP-H from where? You have added the electrons, there is even some energy, and remember there are hydrogens which were lost from the breakdown of the water. Don't forget, at photosystem 2, those hydrogen ions now, which were coming from water, now rejoin. They are going to be added over now to NADP. Now, we have electrons, we have hydrogen ions. Now, when you bring all of them together, we are going to form what we call the leucinide. Now, so far, what have we yielded? We have yielded what we call NADP-H, or leucinide, and ATP. Now, both of them are going to be taken to what we call the Calvin cycle, the Dakar reaction in C3, as well as in the C4, H and Slack is what? Cycle. Now, they are going to be acting as the energy sources now, or the hydrogen sources. You have ATP as energy source, and the leucinide as hydrogen source, which is going to help in reduction, and the other one will help now to accelerate other reactions as we are manufacturing our glucose. Don't forget that. Now, in the summary, guys, don't forget this. If you are going to deceive yourself that you have grasped the content, one, we have to understand that in the non-cyclic photophosphorylation, there are two photosystems. That is photosystem 1 and photosystem 2. Don't forget that the photosystem 1 at 700 nanometers, photosystem 2 at 680 nanometers. Now, 2, we are seeing that we have two electron acceptors, two primary electron acceptors. We have plastoquinone and ferredoxine. Don't forget that. What are we yielding? We are yielding ATP and NADP-H2. In that one time, we are going to compare the cyclic photophosphorylation and non-cyclic photophosphorylation. So in summary, that's what we can talk about non-cyclic photophosphorylation. Try to follow up the notes properly as they are moving on your screen. Follow them up. The chain is clearly illustrated. I've even put a model for you of the electric pose now. Try to look at that model. It is that animation where you have two ladders, and you are seeing the main. They are now on the top. One is at the top of the ladder, another on the top of the second ladder. Both of them acting as electron acceptors. Don't forget. The first one acting as plastoquinone, the second one acting as pyridoxine. Then you see that green part acting as photosystems on those ladders. Those ones can depict a clear image of what we are talking about. Don't forget that energy is not made, but energy is only transformed from one form to another. Here we are just transforming for energy from the sun. And when we take it, the food we are eating, that is the carbohydrates, but via the glucose. Don't, as a scientist, that one should be on your mind. So